Okay, so I was on the bus with Larry and Kaylee and Claire Ellis. Claire Ellis didn't understand all the parts of the calculus conversations we were having, but we were talking on the bus on the way home from Winona. And Larry did mention to me that, I talked to them about, just how hard you work as a teacher to try to help people remember things. And one thing I plan on doing next year is in pre-calculus and calculus, if you want the 2% extra credit for the study guide, there will be an additional page of all material that is just reviewed. And then one of those review questions will be on the test as well. That way it will force people to continue to go back and do the stuff over and over. And it's things like this. For example, some of you guys, when you're looking at this problem, 2x plus y equals 6, and you wanted to graph that, you should be able to do that without putting in slope-intercept form. You should be able to look at this, y is 6 and x is 3, and things like that should hopefully come pretty quickly to you. Now, I know that the more we practice that, the better off it'll be. But that's graphing lines. The question is, how would you guys do with things like logarithms? And Larry admitted, he said, I don't really remember anything about logarithms. Well, the part of calculus that we're headed to right now, and a lot of calculus too, so we're completely done with the red book. We don't need to, no, I need them for next year. We will not burn them. Yes, I would like you eventually, please bring your calculus book back. I do need it. Okay? And I'll give you a new green one. Anytime would be fine. Shh. But we need to review. Shh. We need to review logarithms, because my guess is you don't remember a whole lot about them. And these are some interesting formulas that deal with logarithms and exponentials. These pieces are parts that you would like to maybe keep as notes. If you have your calculus note sheet, take that one out, the one I made for you guys. Where is it? Take it out. Take it out. Yeah, there you go. So this one right here that Haley Schrader has, I'll give you a better one, but I think that this one's pretty good. And if you notice, there's a lot of logarithm stuff at the bottom, isn't there? Those are the most important logarithmic equations, relationships that you're going to use. So, today is not a day to kind of zone in and zone out. We're going to move really fast because this should be review, okay? Are you ready? Let's go. Express the following equations in exponential form. Exponential form, okay? You have a base, you have an exponent, and then you have the number. Which one's the base in this problem? Very good. 2 to the 3 equals 8. I think Nelson taught you this loop-de-doo thing, where you go 2 to the third is 8. Whatever. Okay? I don't care how you think of it. The way I think of it is that logarithms solve for exponents, so I know the number on the end is the exponent. I also know that this is the base because we always call it the base. That's how I think of the problem. So this is 5 to the fourth is 625. So let me read off the next one. What is it? Does that make sense? If it's negative, it goes down to the denominator. What would the next one be? Okay, good. So that's the most basic fundamental principle of logarithms, that you have to be able to express them in that way. Okay, you need to be able to think of them in a way that you can understand. Now it says express the following equations in logarithmic form. So 3 squared equals 9. That's the way you would like to think of it. Let's think of it as a logarithm. What would we have? Log base 3 of equals 2, because the exponent is what you solve for. So what's the next one? Well, so logs can equal 0. Log base, do I have to write the 10? No. Of equals negative 4. And last one, log base m of p is equal to n. Solve for x. Anybody see A? It's 2. Because 3 to the x is equal to 9. That's how we think of it. What's the base for natural log? E. Oh, you don't know the magic of E yet. Now that we know limits, we should really look at the magic of E. I'll show you tomorrow. E is a very special number, about 2.718. Okay, and we say that E to the x power is equal to 1. What do you raise a base to in order to make it 1? 0. Very good. X is 0. What number do you take to the third power? You get 216. Something to the third power is 216, and yep, x is 6. 2 to the negative 4 power is equal to x. (16) 2 to the fourth is 16. See if you can do the last 4 on your own. Go. What's up? Just gotta be smarter than the problem. Right, so they have the same base, right? They have the same base, and the exponents have to be the same, right? So 3x has to be equal to 2. So therefore, x is 2/3. What you guys did is you said, but you thought about 2, right? Yeah. Okay. All right. So now we have different relationships between logarithms. For example, that's really getting annoying, isn't it? I'm getting an email. Right. This Nelson has nothing to do with it. Cherry hour. Just play. Alright, so let me just help kind of get your mind in order here. Don't write this down. X to the third times x squared. What do you do to the exponents? You add them. And so you can see when you're multiplying, you add. And since logarithms solve for exponents, we can pull logarithms apart by substituting addition and subtraction. So at the front page, we had all of these laws right here, and you remember using them last year. This is what we're going to use. Okay? So I know that this is quick. If you need help seeing this, let me know. But this is the same as log base 3 of 4x minus. Very good. So it says, write the following in form of no logarithm of a product, quotient, root, or power. I currently have a product. How do I separate that first one? Good. See if you do B on your own. A little tricky. That should be letter B. So if you have an exponent, the exponent can move out front, right? Because if you have a power to a power, what do? Power to a power, you multiply. So you can see we take that power and we multiply. Because logarithms solve for exponents, so that's what you do. All right, next one. What should I do first? To what? 1/2. Very good. Move the 1/2 out front. Larry sees it. This is the first step. 1/2 log base 8 of 8 over got ahead of myself. 8 over x plus 1. Yes, you do. Very good. So I'll write the 1/2 outside in parentheses so that it's log base 8 of 8 minus log base 8 of x plus 1, that quantity. Now we'll see who really sees the one last step that I should do. What's log base 8 of 8? 1. So if you get something that simplifies, you should do that. So you get 1, so you could write it then just 1/2, because 1/2 times 1 is 1/2, minus 1/2 log base 8 of x plus 1. So we understand why log base 8 of 8 is 1. 8 to the what power is 8? Alright, what should I do first for D? This is complicated. Yep, log of 3x squared plus log of cubed root of 2y. No. Split it up again. Log of 3 plus the log of x squared, because the 3 is not being squared, so you can't move the squared out front yet. Plus, you can move the 1/3 out front now because everything is being taken to the 1/3 power. So 1/3 log of 2y. Need to change anything here? No, log of 3. How about here? 2 log of x. 1/3 times, parentheses, because it's got to carry all the way through, log of 2 plus log of y. So those are the relationships to logarithms that you need to. If you would like to put a 1/3 log of 2 and a 1/3 log of y, that would be fine. Same thing. Any other? Okay, use laws of logarithms to write them as a single logarithm. So now we're going to put them all together to write them as 1. You see what the first one's going to be. Good. Natural log of 120 over 4, which is the natural log of 30. Is it coming back? I mean, are you like, okay, there's some familiarity. Okay. Okay, so why don't you try B on your own, see how much progress you can make with it, okay? Okay, we're going to connect to make this as plain and simple as possible. Think about this, people, okay? Logarithms solve for exponents. If an exponent is positive, does it go in the numerator or denominator? Numerator. If it's negative, it goes in the... So you can see that this expression here is negative. So that means it has a negative exponent value. So we will move it to the denominator. Whereas these two are both positive, so they'll stay in the numerator. That's how you can kind of think about it, all right? If you would like to change it to 3 log base 7 of x plus 2 log base 7 of y, and then subtract at the end, if that would help you think about that, you sure can do that. This just ends up being log base 7 of x to the third, minus log base 7 of 4, plus log base 7 of y squared. And then once I have that, I just have addition and subtraction, so all I do is log base 7. I put my positive ones up top and my negative one down below. That's it. How's that? Let's skip those 2 problems. I don't want to. We don't need to waste our time on that. Calculator, get your calculator, get your calculator. All right, so now we got to think about solving these type of equations. We need to get the x by itself. So if we want to get x by itself, what has to move? The 5. So we have this wonderful operation we can do now. As long as we do the same thing each side, we're fine. If I do this, log base 5 of 5 to the x, that will be equal to log base 5 of 30. You know what this reduces to? This just becomes x. Log base 5 of 5 to the x, these cancel. If you're wondering why, because if you were to actually work it through, log base 5 of 5 to the x equals something, right? That means 5 to the something is equal to 5 to the x. What's that something? Something is equal to x. So anytime you have this, those are inverse operations. Logarithms and exponential functions are inverse operations, so you can just get rid of them. Just like if I asked you to solve 2x equals 8, and you multiply both sides by 1/2, 1/2 and 2 are inverse operations of multiplication, right? These are inverse operations of each other. That's why that works out. So we keep that in mind. So we end up with, as you said, x equals, you can't do log base 5 on your calculator. Well, some of you can. I know you guys have a log, change of base formula on your TI-84s. Great, good for you. So happy. So if you're back in my day and you didn't have anything like that, how would you do this? You don't have to use natural log. You just use log, but it doesn't matter. But somehow, what you do is the change of base formula is take, some people say the log of the top divided by the log of the bottom. It's just the base goes on bottom and the number goes on top. So try natural log of 30 divided by natural log of 5, or log of 30 divided by log of 5. Doesn't matter. You're gonna get the same thing. You do log base pi of 30 divided by log base pi of 5, and you come up with the same thing. Just as long as your base is the same, you're going to come up with the same answer. What do you get? Radians or degrees. Yeah, that'll make a big difference right now. So does that make sense that 5 to about the 2.11 would give me 30? Why does that make sense to you? Because 5 squared is 25. So, all right. Try letter B on your own. Try B on your own. Go. You can. You can do it. You can do B. Don't divide by -2 first. Subtract 5 first. Then divide by -1. What do you got? 5.55. That makes sense? It's kind of a mark of an esteemed mathematician. Natural log is it's very friendly, It's just very friendly. All right, to answer Larry's question, you guys will like this. Okay? Answer Larry's question, why do I like natural log? If you take the derivative of natural log, you know what you get? It's on your sheet. 1 over x. But if you take the derivative of that, get that. So, I like that better. I like to work with natural log when it comes to calculus because it just works better. So it's just kind of habit. Number C. Letter C. Let's do it. E to the 2x plus 4. What do you do first? Equals 42. I gotta get at the exponent. So what logarithm has a base of e? So natural log of e to the 2x plus 4 equals the natural log of 42. I just took the natural log of both sides. What happens to the left side? Bam! So you get 2x plus 4 is equal to, what's the natural log of 42? I need a number. It's just a number. What was it? So now can you solve that? That's a piece of cake. Upside down. It sounds like post-prom party is to watch Stand and Deliver. So Larry's house. Everybody join in. All I know is Saturday night, me and a bowl of popcorn and desolation and smog. That's Saturday night. I can't wait. I can't wait. No prom duty for me. I had prom duty a few years ago. Oh no, he's rebelling. Uh-oh. All right, here we go. 4 to the 2x equals 3 to the 6 to the 3 minus x. What do I do now? I don't see an e, so I'm not going to use a natural log. Larry, I'm going to use a log with a certain base. What base would that be? Okay, good try. We're going to do log base 4 of both sides. Whoop. Watch the trickiness. What happens to the left-hand side? 2x. The right side looks messy, doesn't it? Do you see what you do? Yeah, she got it. Put the exponent in front. Yeah, log of 6 divided by log of 4. Give me a decimal. Somebody. $1.29. We'll distribute our 1.29 through. 2x equals, what's 1.29 times 3? Add a 1.29x to both sides. I get 3.29x. Equals 3.87 divided by 3.29. That's pretty cool, huh? Larry, on a scale of 1 to 5, how cool do you think that is? All right, let's flip to G. Now we got the X there. If all right, log base 3 of x is equal to 2. Now you could write it just in normal exponential form, be able to figure it out, but I want to show you the inverse operation. If we used to use logarithms to get rid of exponents, then I could do the opposite. So, because we don't have time for it, and it's really not important. Look at what I did there. I made each as an exponent. So if they're inverse operations, what's going to be left on the left-hand side? X. They're inverse operations, right? Just like those are inverse operations of each other, right? Just happens to be. All right, what do you want to do first to this side? Divide by 4, log base 6 of x minus 3 is equal to dose. Yep, raise it all to the 6th, or as a base of 6. $36. Letter I, what do you do first? Minus the 7, 2, natural log of x equals 1. Now what? Divide by 2. Natural log of x is equal to 1/2. How do I get rid of the ln? Make a base of e. So x is equal to e to the 1/2. Or x equals the root of e. I don't even want your decimal. I've got the root of an irrational number. That's kind of cool in and of itself, right? I mean, like that. It's like the root of pi. I mean, it's kind of exciting. Larry, how excited is that? Okay, let's get to a more complicated problem. Do just a couple more here. What about j? We need your ingenious here. What do I do for j? Very good. Natural log of x over x plus 2 is equal to 3. So now I have one logarithm. Now I make it a base of e. X over x plus 2 is equal to, what is e to the third, Elizabeth, 20? How do we solve that? Solve. X equals 20.09x plus 40.18. 1 minus 20.09. 19.91. Did I do something wrong? Is it 19.09? Did I make a mistake? Okay, 40.18 divided by 19.09, what do you got? Alright, so, what did you say? 02? Okay. Oh. Just by chance. So, you notice that we don't have to do the last two. I just want to do the graphing on the back side. You don't have an assignment today, but this is just one day to practice logarithms so we get back in the flow. No. That's just sine cosine. You did it? Oh, let's sleep. Boys and girls, what is, okay, let's think about how this is formed. What is 4 to the 0 power? 1. So it has a y-intercept of 1. What is 4 to the 3rd power? 64, yeah, it's a big number. It's somewhere way up there. What is 4 to the negative 3rd power? Yeah, 1/64. So you can see, by just plugging in 3 numbers, we can see that this graph is going to have that type of shape. It crosses through 1. In fact, that's the parent function for all exponential functions. They'll cross through 1 on the y-axis, and they have a horizontal asymptote of y is equal to 0. You can't ever get out a value of 0 or a negative value. Okay? Now, if you think about it differently, 1/4. 1/4 to the 3rd. 1/4 to the 3rd, very small. 1/4 to the 0. 1. 1/4 to the negative 3rd. Big number. So, if your base is less than 1, you can see you get the reflected graph. So we'll just fly through these. Y to 2x. Is it going to look like A or B? A. So it doesn't really matter other than trying to draw the asymptote correctly and having it pass through 1. Okay? That's really the important part. Because calculus is talking about rate of change, and so we like to think about the graphs, the rate of instantaneous rate of change, the area bounded by the function, all that good stuff. What do you think happens if we stick a negative in front? What does that do? Flips it. Vertical flip, right? So it's going to look like this. What if we subtract 4 off the end? Down 4. So instead of passing through at 1, it's going to pass through at negative 3. And its horizontal asymptote, instead of being at 0, is going to be down here at negative 4. So this graph is going to look something like that. Alright, so the graph normally crosses through 0, 1. If you have a x minus 2, that's going to shift it how many units? 2 units to the right. And then the plus 1 will shift it 1 unit up. So instead of going through 0, 1, if you shift it 2 to the right, 1 up, it will go through 2, 2. If you got a plus 1, does that change the horizontal asymptote? Yep, horizontal asymptote is up 1 as well. And then the 2/3, is it going to start up and finish down, or is it going to start down and finish up? Up and finish down. Something like that. So this way you can at least, at least if you type the graph in your calculator, you at least have a general idea of what to expect. That way you know if you did something incorrect or correctly. Let's look at G, and we'll finish these off. This will be real quick. A log base 3 of x, okay? The logarithms are a reflection. So, for example, if they're inverses, if you remember from pre-calculus, you had a great pre-calculus teacher, an inverse is a reflection over the x-axis. And since exponential functions and logarithmic functions are inverses, the logarithm is going to look like this. Instead of passing through 0, 1, it passes through 1, 0. The x and y values switch for inverse functions. Remember last year where we did y equals 2x plus 3, and I said find the inverse, and you said, oh, well, x equals 2y plus 3, and then you solve for y. So that's what happens. You switch the x and the y, and so it ends up going like this. You have a vertical asymptote of y equals 0. I'm sorry, x equals 0, and it passes through 1, 0. That's what the graph looks like. So if I subtract 2 off the end, is that going to change the vertical asymptote? No. Instead of passing through 1, 0, it passes through 1, negative 2. We don't really know where it crosses through the x-axis. We would have to figure that out at some other point. It will, but what's the shift going to look like for I? 3 to the left. So instead of going through 1, 0, it goes through negative 2, 0. And it has a vertical asymptote here. What's the vertical asymptote? X equals negative 3. 3 units back from the other one, which was x equals 0. Very good. So you can't have any values over on the other side. Remember, discontinuity is an important idea in calculus. We got to really think about the domain and the range. What happens if we put a negative in front? It flips. What happens if we put negative in front and you got an x minus 4? 4 to the right. 1, 2, 3, 4. So go over to 5. Right? And we have a vertical asymptote then at positive 4. Okay? Now we'll leave it at that. Was this helpful? To at least see some logarithms again? Otherwise, we would have just started fresh right into it like, hey, that would have been bad. Okay, so tomorrow we start the calculus. Hold on to this review sheet. It'll be helpful. Megan, we miss you. Watch the Desolation of Smog.